Okay, welcome everyone to our October midrc seminar. We're joined today by Dr. Praveer Singh, and he will be taking us on a CycleGAN journey. So that for sure sounds very intriguing. And of course, the topic of race is very near and dear to the Bias and Diversity Working Group of midrc. So this will be a very relevant and interesting presentation. But before I introduce the speaker, let me remind everyone that there will be a live Q&A session at the end, so Dr. Singh can answer all your questions. So feel free to put those in the Q&A box while the seminar is ongoing so that we can get to all your questions in the end. So Dr. Praveer Singh is currently serving as an assistant professor at the Division of Artificial Medical Intelligence within the Department of Ophthalmology, University of Colorado School of Medicine, where he is also a member of midrc investigator Dr. Jayashree Kilpathi-Kramer's lab. Before joining University of Colorado School of Medicine, he was a postdoctoral research fellow at Harvard Medical School, where his research involved developing novel AI tools for applications in radiology and ophthalmology. Okay, Praveer, the floor is yours. Take it away.
Thank you so much, Karen. Let me share my screen. Are you seeing the presenter view or are you seeing
Yes,
the main slides?
that's good.
Okay. All right. So hi everyone. I'm Praveer Singh. As Karen introduced, I'm basically a faculty within the Division of Artificial Medical Intelligence at the Department of Ophthalmology. And today I'm going to talk about decoding race in medical imaging through a CycleGAN journey. So I have no disclosures for this work. So giving a brief background around bias in artificial intelligence, we all know that various undesirable biases and injustices exist in the society, be it racism, socioeconomic disparities, and it has been widely acknowledged that healthcare professionals are kind of prone to conscious and unconscious bias related to patients' gender, age, sex, race, and thus potentially influencing the diagnostic and subsequent treatment decisions. With the growing use of AI algorithms in clinical settings, there is increasing concern about the potential biases in AI algorithms as they may be deployed on a larger scale and across diverse populations, thus posing a heightened risk of transferred harm. Models trained on data containing biases will make obviously biased predictions. Even AI trained on unbiased data can be unfair due to design choices, evaluation metrics, and labeling schemes. And finally, the biased algorithms can actually perpetuate and amplify existing inequalities within the society. So there are different types of biases. Biases can be in the data set. For example, the selection or representation bias in terms of failing to collect representative samples from intended population. There can be measurement biases. For example, the cameras with limited dynamic range may not capture the darker skins. Historical biases might be there in terms of past data that encodes past biases and normative values. There could be biases in terms of algorithmic development. So, for example, the problem frame, like choosing one particular objective or one particular predictive task or intended use of the model over another one. Proxy features could introduce biases that features in terms of that are correlated with sensitive attributes such as race, sex, or socioeconomic status. Evaluation can also lead to bias in the algorithmic development, and both evaluating and testing the model according to one metric and not another metric. And then there could be biases in terms of deployment and application. So basically having feedback loops where your AI model can affect the clinical decision making, which in turn can affect patient outcomes, which further affects healthcare data and which is then used to train the AI models. And finally, uh, uh, having like the appropriate use case, for example, using AI trained only on data from US, and trying to test it on Indian population without additional fine tuning can also lead to biases in terms of deployment. There have been various tools developed in the past. The midrc bias awareness tool, which was developed by this midrc bias and diversity working group, actually identifies potential sources of bias and provides descriptions, impacts, real-world examples, measurement methods, and mitigation considerations for the different steps along this medical image analysis AI machine learning pipeline, be it data collection, model development, data preparation, model evaluation, or model development deployment. So what is the motivation primarily for our work? So basically, there was this recent paper from uh, Judy Gichewa and her fellow collaborators. Judy is basically one of the midrc investigators and part of the bias and diversity working group. So as we continue to develop AI systems, we seem to be learning that AI does seem to have like superhuman capabilities in that it can seemingly excel at tasks that humans are not able to do. So while existing evidence suggests that visible light spectrum images, for example, your skin or your retinal fundus photos, might contain pigmentation or melanin-related details linked to race, it was commonly believed that non-visible light imaging modalities, for example, the chest X-rays or CT scans, probably lacked such information. And basically, this was actually a pretty cool work done by a large international group of researchers, including Judy, that showed that AI models can reliably detect self-reported rays from non-visible light imaging modalities such as chest X-rays and CTs. They further actually explored a variety of different potential experiments, including downsampling the images, looking at different high and low pass filtered images, but were unable to determine how the algorithm was so successful. So why is it actually relevant? Like the model can predict race. Why is it actually relevant for our downstream task? I mean, the racial biases, we have seen racial biases leaking into healthcare algorithmic developments when proxy variables such as healthcare spendings are used to train these models. Uh, Zayed Obermeier's group actually experimented with a model that was intended to predict risk scores to determine which patients would need extra medical care. However, previous patient healthcare spendings were used as a proxy label for training this specific model. And given the fact that less money is spent on Black patients than white patients for the same level of need, removing this racial bias increased the percentage of Black patients receiving additional help from 18 to 47%. Similarly, Marze Ghassemi's lab has also actually showcased racial biases in medical AI. Their work in check exclusion, which actually showed that true positive rate and the differences in true positive rate are, can be used to examine the biases with respect to protected attributes such as patient sex, age, race, and insurance type as a proxy for socioeconomic status. And a high true positive rate disparity indicates that, for example, the sick members of a protected subgroup would not be given correct diagnosis at the same rate as the general population, even in algorithms with high overall accuracy. So what they found was that the most unfavorable subgroups were females, Hispanic population, and folks with Medicaid insurances. And similarly, subsequent work from their lab actually showed that classifiers produced using state-of-the-art computer vision techniques consistently and selectively underdiagnosed, underserved patient population, and that this underdiagnosis rate was higher for intersectional underserved subpopulations, for example, the Hispanic female patients. I mean, we have also seen issues of bias in dermatology, where researchers have outlined the potential dangers of using skin cancer detection algorithms for darker skinned patients. Even in medical devices such as pulse oximetry, we have seen biased measurements. I mean, this was a running issue during COVID, where devices were displaying higher oxygen saturation than the actual ground truths for darker skinned patients. Another relevance in for predicting self-reported race could be in terms of threat to privacy, thus exposing patients to risk to re-identification. So, I mean, this recent work actually showcased that imaging features used by a deep learning patient re-identification model for chest radiographs actually corresponded to intuitive human interpretable characteristics like patient sex, age, and weight. And changes in these identifying features over time may act as biomarkers for emerging abnormality. So now that I have provided you a motivation for this study, the aim of this study was actually to decode which imaging features are relevant for predicting self-reported race. And we actually introduced a novel method to highlight image regions relevant to the task of race prediction. So in terms of past interpretability methods, I mean, there have been methods that could visualize features directly. For example, like uh, in the past, researchers tried to understand how a neural network functions internally by studying what each of its neurons has learned to detect. So one such method, which is outlined in like the reference one, basically used activation maximization, which actually synthesized the input, for example, an image that highly activates a specific neuron in the neural network. There are also saliency map techniques, which have been quite popular in the past, but some of the works including from our own group, have shown that these are quite untrustworthy given their lack of trustworthiness in terms of localization utility, sensitivity to model weight randomization, repeatability, and reproducibility. And finally, there are these occlusion map techniques which highlight relevant image regions by occluding specific independent regions in the image and plotting the corresponding change in prediction probabilities spatially throughout the image. And the more the change that you see in the prediction probability, the higher is the relevance of contribution of that region towards the model's prediction probability. So in terms of our own method, we actually used CycleGAN technique, which is actually quite popular in the computer vision literature, in order to transform an image from a patient with self-reported race of Caucasian into an image from a patient with self-reported race, which was Afro-American. So CycleGANs are models which have been introduced for image translation and basically in an unsupervised way. So you have the input A, which is, for example, here the horse, which is translated from domain A to domain B, which is a zebra. And you have a cyclic consistency loss that actually minimizes the difference between the generated the finally generated horse image and the input horse image. And similarly, you can also have the input zebra image, which is actually having a cycle consistency loss with the generated zebra image. So we actually use the same technique, and once an image has been transformed from one race to other, we took the pixel-wise difference, and basically the difference map highlights the pixel whose values should be changed significantly to flip race prediction from one race to another. In terms of experiments, we actually use the most popular, the mimic chest X-ray dataset, which had 150,000 Caucasian patients and 36,000 Afro-American patients. And we split the dataset into training, validation, and test splits on a patient level. We used a race prediction model in terms of a ResNet 34 model to predict race. And we actually computed the difference maps for images between the image whose race is correctly classified, and the second image whose race is incorrectly predicted after being transformed by the CycleGAN. In terms of baseline, we actually used occlusion map technique, which I outlined in the past. And we also did a gender-based subgroup analysis to check whether difference maps differ based on gender or not. So in terms of occlusion maps, we saw that, I mean, here we see occlusion maps for images where the predicted probability of the correct class is greater than 0.99. And as we can see that for both the classes, be it self-reported Caucasian or self-reported Afro-American race, the change in probability was very minimal, like around 0.1. And we cannot actually identify relevant regions in the images because of that. Whereas in case of difference maps, uh, where we actually bend the difference maps based on the prediction probability of the incorrect class from the CycleGAN generated image, we saw that the relevant regions are basically highlighted around the neck, lungs, as well as arms. And the relevant regions are the same across the probability bins, though the differences became smaller as we moved from higher probability to a lower probability of predicting uh, the alternate class. So in the image, if I can outline it, we are actually, for the top row, we are converting an image of a white person to an Afro-American person. And the predicted probability is basically for the Afro-American, which is in the first column is basically greater than 0.99. In the second column, it falls between 0.99 and 0.9. In the third column, it's between 0.9 and 0.5. And in the final column, it's less than 0.5. So, and it basically is the same for in the opposite direction also when we move from Afro-American to the Caucasian. So, and the relevant regions remain around the neck, the lungs, and the arms. And I think Judy's work actually also showcased that the lung region were actually the least relevant in terms of predicting race, whereas in our case, these are probably the most important regions, including the neck area, to predict race. We also did a gender-based subgroup analysis where we actually looked at difference maps for both female as well as male gender with probability of the incorrect class on the CycleGAN generated images. So the incorrectly classified as the first row shows incorrectly classified as Caucasian, whereas the second row shows incorrectly classified as Afro-Americans. And in both the cases, the neck and the lung areas remain relevant regardless of the gender type. And also the map intensities do change across genders, especially for the Caucasian patients, which is highlighted in the top row. So broadly, I mean, I'm not a medical physicist, but talking to some of the clinicians in the group, we actually, I mean, a broader hypothesis was that there are certain automated exposure control in X-ray machines, which actually calibrate the X-ray beam to the intensity of the photon beam being detected after having passed through the patient. So if there is more soft tissue to attenuate the beam on average, I mean, the X-ray beam will be adjusted automatically to be strong. And if there is one area that we would be easily to pick up differences in soft tissues, it could be the neck area. And so probably we feel that that could be one of the reasons why the model was picking up the region around the neck so prominently. So to conclude, I think in this work we address the lack of effective interpretability methods to identify image regions relevant for race prediction from chest X-rays. We introduce difference maps, pixel-wise differences between an image and its CycleGAN generated version, for which a race classification model actually predicts the incorrect class or incorrect race. We showed that difference maps are better able to identify relevant image regions than the occlusion maps. Difference maps actually highlight similar regions for both male and female patients. In terms of limitation and future work, we gained uh, in terms of interpretability at the cost of needing to train a CycleGAN model. We tested our method on one prediction task only. I think the next steps would be to expand it to other demographic features. We ran experiments on one public dataset, and I think we would be willing to include additional datasets, both public as well as private. And I mean, this work came out, the work on the right actually came out recently, and which actually demonstrated that technical parameters related to image acquisition and processing, for example, like the window width, the field of view, and the view position actually influence the AI model's predicted power for patients' race. And they also actually showcase certain mitigation strategies. So combining our interpretability technique with some of like these works that are investigating as acquisition parameters would be actually something for future directions. And finally, I think in terms of, I mean, this other work that came from Judy and other folks, I think was the model actually trained, they trained a model using augmented images, and it was less likely for such a model to be influenced by demographic information in detecting image level labels. So I think like having a more targeted image acquisition, image augmentation technique in order to prevent this shortcut learning would be actually quite relevant in the future to prevent any sorts of induced biases into the model. So finally, I would like to thank all my contributors, mostly Lakshika, who was one of our master student in our lab and who actually was running hands-on on all the experiments on this project, and then Ken, Matt, Giacomo, and Jayshree, who were also part of this project. So thank you.
Thank you very much for this very interesting presentation. And audience, please put your questions in the Q&A box. I'll get started with a couple of questions, but please don't hesitate to ask questions. So yeah, I'm was a little confused. So you mentioned about your interpretability maps. You were showing that the neck and the arms, and I forgot what the third region was, were important for the algorithm. Oh, the lungs, yes. So can you elaborate a little bit more on that? Maybe you can bring back up those slides, because you only showed them for where the algorithm was wrong, right, in predicting race. But what about if it was correctly classified? What would a map look like then, for example?
So I think the idea, I think this could be confusing in a sense that incorrect classification means that the model was actually able to correctly switch from the input class to the final class. So, and when we are actually doing that, and if we are doing that with a high probability, it means that those are the specific regions which are actually leading for the model to um, to switch classes from the input class to the final class. So yeah, any changes in the areas which are happening in either the neck or basically the lungs uh, or the shoulder regions actually are causing a significant switch in the prediction probability from, for example, from the white class to the Afro-American class.
Mm-hmm. Right. Okay. So my question was, how does it look if it switched like incorrectly, or it didn't switch?
Yeah, I think I mean in that case, I think it's basically the one on the very right, the image on the very right.
Okay.
So your difference maps are way more pale, and I think those regions that we identify in like correct classification are basically now like uh, merged into the entire image. So there are no significant regions.
Okay.
Yep.
All right. Yes. Okay. Thank you very much. That helped me a lot. Okay. So now let's move on to some questions from the audience. So the first question is this race or is this BMI being detected? BMI is related to income, which is correlated with race.
Yeah, actually, that is a very good question. I think we have also, I mean, that is one of the next steps that we are thinking because the soft tissue that is attenuating the beam could be related to the BMI of the person. So, I mean, that would be one thing that we probably would be investigating next. That is it the confounding, is it the BMI of the person concerned, and is the BMI directly related to the soft tissues in these areas, which is actually impacting the model to predict the self-reported race.
Okay. So there's a related question from a different audience member. Did you match the data sets to avoid confounders? How did you prepare or curated the data set for training the CycleGAN?
So yeah, I mean, in terms of matching the data sets, we just matched it on the basis of age. But otherwise, I think we could have matched it on the basis of BMI also, which we actually didn't do. So it was just based on the age that we matched the uh, the Afro-Americans and the white population.
Okay, not by sex either.
I I think it should be based on sex also, but I'm actually missing those details.
Okay.
But given the fact that we actually did a gender-based subgroup analysis, so I think we
Mhm.
also did it on the basis of sex.
Okay, so another related question. So was there a division of the data based on PA versus AP view? So not as sick versus sicker patients, right? The portable ones who get a portable X-ray tend to be sicker because this mimic data set contains both.
Right. So I think can you repeat that question? Sorry.
Was there a division of the data set based on the PA versus AP view? So between regular acquisitions and portables, basically.
Uh, Unfortunately, I cannot answer that question, but I think we mostly use the frontal views for this analysis.
Okay, that's something worth looking into for
Yep.
sure, right? I mean, if you get a portable X-ray, you tend to be sicker, which might be
Right.
correlated to other, social determinants of health, for example. Okay, okay, at this time no audience questions, so let me ask you another question in case somebody's still typing. Um, So it's more of a philosophical question, I think, but we try to emphasize, we try to make our AI unbiased or as fair and as high performing as possible. But do you think that, fixing this on the AI side, will this impact like how radiologists or other clinicians, will that do away with the biases when there is interaction between AI and human, or are there different things that you need to take into account except for just fair AI? Is that going to be enough?
Yeah, I think that is a quite pertinent question. I mean, currently we aren't even sure if the biases are coming from the underlying data or is it basically uh, uh, coming from the model actually picking up uh, random spurious correlations, not specifically um, for the race of the patient. And I mean, based on that, I think it would be actually pertinent to first identify what are the issues which are actually causing the model to predict race. And once we have identified those, probably we can delve into either going in onto the dataset side or the model development side. If it's the dataset side, I think we already have like existing issues in how the the healthcare professionals identify uh, these different racial or gender or these different categories when they are reading uh, uh, these chest X-rays versus if we are actually going with an AI model, basically predicting these models, these different these features, be it the race of the patient or the chest X-ray. Oh, sorry, uh, the age of the patient. I think that so what I'm trying to say is that both of these are actually two different things. So I mean, the first thing is to actually identify whether it's coming from the data side or is it coming from the AI model side.
Okay, yes, thank you. So there is another follow-up comment from one of our earlier question askers. Just a comment that AP and PA views are both frontal, right? One is taken when the patient is standing, and the other one is when the patient is supine, like in bed. So that was just a comment. I don't know if you want to comment more on that. So this was regarding whether you curated the data set for the different views, like PA versus AP.
Yeah, I mean, I have, as I said, like, I feel like it was, we used both the views, AP and PA both, but we haven't like secluded one view from the other view. So, yeah.
Okay. Yes, thank you for the clarification. Okay, let's see if there are any more questions. Okay, no, one of says thank you. Okay, so let me ask one last question in case somebody's still typing. So this is just because you mentioned it. This is slightly unrelated to your topic here, but you mentioned the risk of re-identification. So how real do you think this risk is, like at large, if somebody does not know that I got a chest X-ray in California, for example? How real is the risk of patient re-identification?
Yeah, so I think that is a fundamental question. I mean, given the fact that re-identification can happen mostly when you have an existing database which has like all the demographic information. So, I mean, even in case of ophthalmic images, we were able to re-identify patients with a very high accuracy with retinal eye photos. And same, I think they have shown it for chest X-rays. The question is, do we have an open source database, for example, the one that we find, for example, the iris database that we see like in case of airport scrutinization. So that is the main thing. Like if we can have such an open database which has like all the demographic information and also the patient information, and can we use that open database using a query image and re-identify that patient and then track it back to the existing markers of that patient to identify in terms of where the patient is located and all those things. But yeah, I mean, the re-identification risk, personally, I feel like is a incurrent, pertinent risk, and I think we should be aware of that. And but from our initial preliminary experiments, we have seen that we can predict the demography of the patient, but in terms of re-identification in chest X-rays, we found that the recall rate was pretty low, though the recall was pretty high in case of retinal fundus photos.
Okay, so I from my understanding, then it matters, like if there's information available outside of, say, the medical field, such as like the airport security screening, then it might be much easier to re-identify patients. Okay,
Right.
that's very interesting. Okay, there are no further questions. So with
Though
that, we
if we
can.
are though if we are able to link any of these, either the chest X-rays or the retinal photos to your external face photos, which are also present on Facebook, I think the re-identification becomes quite easier. So yeah, I think that could also be like a future work, like if we can uh, basically match any of your either the chest X-rays to the facial photos of a person.
Right.
Uh,
Yeah, that would be interesting.
yeah,
I don't know how well it would work, but yeah.
yeah,
Definitely interesting for sure. Okay, so there are no further questions in the Q&A box. So with that, we can conclude this very interesting, short and intense seminar. And I would like to ask everyone to join us again next month for our November seminar. So with this, thank you all very much and see you next time. Bye.